Okay, welcome to this second video for chapter 3. In this chapter, we're going to be covering property tables, section 3.5, chapter 3.5. So property tables, what are property tables? For most substances, the relationships among thermodynamic properties are too complex to be expressed by simple equations. So as a result, properties are frequently presented in the form of tables. Often properties are listed in multiple tables. So, for example, superheated vapor table with all the properties when the substance is in a superheated vapor state, or a compressed liquid table when all the properties are in a compressed liquid state, or a saturated region table when the substance is in a saturated state. So, before we get there, though, I think it's important for us to be able to introduce a few properties. So let's start with enthalpy. Right? Enthalpy is what we would call a combination property. Enthalpy is frequently encountered as a combination of internal energy, right, which we have covered earlier, and pressure times volume. The combination is defined as a new property called enthalpy. So enthalpy is represented as internal energy plus pressure times volume, right? So that would be in its extensive form. And then also in its intensive form, which would be specific units, it would be H is equal to U plus P nu. And this is in the intensive form. Often when we look at energy exchanges during a first law analysis, when we do a first law analysis and we bring in properties into the first law in order to quantify energy transfer terms, often enthalpy and or internal energy are used. So let's first look at some examples. So if you go back into your books, in the back of your books, towards the back end of towards the end of the book, you will see several tables, right? There's tables in SI units and tables in English units. First one we're going to take a look at are tables A4 and A5. These are what we would call saturation tables, right? We talked about that saturation temperature and saturation pressure are not independent, right? Meaning that one is a function of the other. So when we look at saturation properties being the properties of a liquid, saturated liquid or saturated vapor, they are often going to be listed as a function of temperature, being the independent variable, which is table A4, or table A5, where pressure is the independent variable, right? So basically, when you look up in the saturation tables under A4, you'll see varying temperatures, and then you have automatically the corresponding saturation pressure, and then listed are the other properties. Well, for the pressure, for the saturation table where pressure is the independent variable, you see varying pressures, and then also the given saturation temperature for that, because they're coupled, right? Pressure and temperature are related to each other directly in the saturation state, and then all the other properties are listed. Before we even look at those tables, I think it'd be important for us to be able to understand some of the subscripts used in the table. So you'll notice that those tables have subscript F, G, and FG, right? F would be what's called the property of the saturated liquid state, right? So this would be the property associated with the saturated liquid state. G would be the property associated with the saturated vapor state. So the property associated with the saturated vapor state. And then FG would be the difference. Basically, it would be the difference between the saturated liquid and the saturated vapor, right? So again, F being the property associated with saturated liquid, G being the property associated with saturated vapor, FG being the difference between the liquid and the vapor. So as an example, if you go back to the tables and you look, you'll see nu sub F, for example, nu sub G, and then there's nu sub Fg. So nu sub F would be the specific volume, right? The specific volume of saturated liquid. Likewise, the V sub G would be the specific volume of the saturated vapor. And the nu sub Fg would be the specific volume of saturated vapor minus the specific volume of saturated liquid. So those are how the subscripts are denoted in those tables. So let's look a little closely at some of these values, right? So here is a little excerpt from the saturation tables, what we call the saturation tables. This would be for water, right? So this would be the temperature-based version. So if we go back, this would be, if you wanted to turn to your books, this would be taken from table A4 in the back of your books. If we look at table A4, we look at, it's increments values of temperature, right? So all the properties are incremented according to temperature. So those are specific temperature points. And then they list the corresponding pressure that has to exist. It has to be that pressure. If you're at a saturation and the temperature is 85 degrees, the pressure automatically has to be 57.868 kilopascals. If the temperature is at 90 degrees Celsius, the pressure automatically has to be 70.183 kPa. Now, that is only for saturation, right? If it's saturated liquid, a saturated vapor, or a saturated liquid-vapor mixture. If you're at a superheated vapor or a compressed liquid, these two values are decoupled, and I can have any combination of a temperature and a pressure, right? I can have not any combination, but what I mean is that these two values are not dependent; they're independent. So I can have temperature existing at different pressures, and I can have pressures existing at different temperatures. But at a saturated state, the temperature and the pressure are linked together. So if I know one, I automatically know the other one. So if you look at it, at the saturated state, right, this value, V sub F, nu sub F, is the specific volume of saturated liquid. This V sub G is the specific volume of saturated vapor. So again, if I'm a saturated vapor, I lie on this line of the saturation curve. So here is a pressure or temperature versus specific volume curve. This is the saturation dome that we looked at earlier, right? This is the saturation line for liquid. This is the saturation line for vapor. So if I'm at a liquid, I'm here on this line. If I'm a vapor, I'm on this line. If I am a saturated liquid-vapor mixture, I'm inside this curve where my specific volume should be at a value greater than the saturated liquid, but less than the saturated gas, because I'm a mixture of liquid and gas. Therefore, my actual specific volume, the combination of specific volume, is going to be a combination value of my liquid specific volume plus my gas specific volume, right? It's not just 0.001032 plus 2.8261. It depends on the mass of liquid and the mass of vapor in it, but I can use that to find what my total specific volume is for a saturated liquid vapor mixture. We're going to look at that later. So let's look at a quick example here, right? Here's that same table, table A4, but expanded a little bit to include more properties and more variations in temperature. So here I have my temperature starting at 0.01 degrees Celsius up to 85 degrees Celsius, right? The corresponding automatic saturation pressure corresponding to that temperature, and then my saturated liquid specific volume and my saturated vapor specific volume, along with the same thing for internal energy and the same thing for enthalpy and the same thing for entropy. These are all the properties, right? Notice that I have my gas enthalpy minus my vapor enthalpy here, right? So this would be 2,500.9 minus 0.001. That would give me this number. So these values are, right, HFG would equal HG minus HF. This is the same thing for internal energy and the same thing for entropy. Why they don't have new FG listed here, I don't know, but it's not. Okay, so there's the table, okay? This would be the saturated water table based on temperature. So the example here is saying take a few minutes and try to locate the following properties, right? I want you to find, for example, the vapor pressure, or vapor pressure is the same thing as saturation pressure of water at 65 degrees. That's what number 1 is asking. So how do I do that? Well, let me go down to the temperature here. I'm going to scroll down until I hit 65 degrees, look at the corresponding pressure. Therefore, my pressure would be 25.043 kilopascals. Right? Okay, great. Assuming that you're good with that, point 2. I want to find the specific volume of saturated vapor at 40 degrees. So I go down to 40 degrees, and it's asking me to find the specific volume of saturated vapor. So I go down and I find that my saturated vapor of specific volume is, my specific volume of saturated vapor at 40 degrees, right? So sorry, I was at 65 degrees there. At 40 degrees is 19.515 meters cubed per kilogram. So my specific volume of the gas at that point is 19.513 meters cubed per kilogram. And part 3 is asking the enthalpy of vaporization at 5 degrees. So what is enthalpy of vaporization? Remember, we talked about earlier that vaporization is the energy released when converting from a liquid to from a gas to a liquid, or the energy absorbed when going from a liquid to a gas. What does that mean? Well, if it's looking for the enthalpy, H, the enthalpy of vaporization, it would just be whatever the gas enthalpy is at saturation minus whatever the fluid enthalpy is at saturation. So if I go to state 5, I can go on over and figure out that my enthalpy of vaporization, HFG, is going to be 2,489.1 kilojoules per kilogram. All right, I hope that's clear. I would take some extra time, go back and look at those tables, and maybe try a few more examples on your own in order to understand that a little bit more. All right, okay, so let's continue. The next slide here we're going to be looking at is what happens when I'm not at just a saturated vapor or not just the saturated liquid. What if I'm at a saturated liquid vapor mixture? I have a combination of both gas and fluid existing at the same time. How do I figure out what my properties are? Right? It's not just going to be the gas specific volume, for example. If I'm trying to find my specific volume of a saturated liquid vapor mixture, it's not just going to be the gas specific volume, and it's not just going to be a fluid specific volume. It's going to be a combination of the both. So how do I figure that out? Well, there's a property called quality. Okay, quality, when we think of quality, we think of like how good something is. Well, in thermodynamics, quality has nothing to do with how good something is. Quality, the word quality in thermodynamics is going to be a property that only exists at the saturated state, right? Quality only makes sense when it's saturation, because what quality is defined as the mass of vapor. Actually, I should probably make that as sub G. The mass of vapor, the mass of gas over total mass, where total mass is going to be the gas plus the fluid. Right? So here, if I have a mixture in this control volume, or in this volume tank, I have both vapor and liquid, both existing at the same time. Well, I have to use my quality, which gives me the percentage of it that's gas or vapor as a function of the total volume. So it makes sense that if my quality is 0, I am a saturated liquid because the gas is 0 when it's lit with a saturated liquid. The quality is 1 when it's a saturated vapor because all of the mass is gas. So it'll be the total of mass of gas over mass of gas, which equals 1. That's only when it's a saturated vapor. Right? And so if it's any combination, if it's between a saturated liquid and a saturated gas, that means that the quality will be at a value somewhere between 0 and 1. So how do we find that total, right? So we're doing a problem and and we're like, well, how can I find out what my quality is, right? Because look at it. Let's look at an example here. Let's take temperature versus specific volume. I have a saturation curve here, and let's say that this is the specific volume at saturated liquid. This is the specific volume at saturated vapor, and I'm somewhere in the middle here, right? My specific volume is going to have a value greater than that of the fluid, but less than that of the gas. How do I find out what that value is? Well, let's go ahead and let's try to do some simple algebra to see how to do that. Okay, so let's say we have a total volume here, right? We have a saturated liquid vapor mixture, right? It's a combination of vapor and liquid. So my total volume of that tank is going to be equal to the volume of the fluid plus of the liquid plus the volume of the vapor. Likewise, my total mass inside of that volume will be the mass of the liquid plus the mass of the vapor. We also can all agree that the total volume is going to equal the total mass times the effective specific volume, the specific volume which is a combination of the vapor and the gas. My volume of fluid is going to equal the mass of fluid times the specific volume of the fluid. And my specific volume of the vapor is going to equal the mass of the vapor times the specific volume of the saturated vapor. All right, so let's go ahead and let's expand this. Total mass, right? This would be total mass. Total mass is going to equal the total specific volume. The total mass multiplied by the total specific volume. This is total volume equals the mass of liquid times the specific volume of saturated liquid, right? This would be the volume of liquid, plus the mass of the vapor times the specific volume of the vapor, and that is the total volume of the vapor. So I'm going to take this equation, and I'm just going to simply divide by the total mass. So I get total specific volume is equal to mass of the liquid divided by total mass times specific volume of the liquid plus mass of the gas divided by total mass times specific volume of the gas or of the vapor. All right, so let's go ahead and let's take this equation, let's bring it to the next slide and continue with our algebra. I know this is not the most exciting thing to witness on a video, but this is really important because this illustrates the definition of quality, which we are going to be using for the whole rest of the semester, or the whole rest of this online class. So specific volume is equal to, I'm just going to rewrite the equation from the prior slide. Mass of the liquid over total mass times specific volume of saturated liquid plus the mass of the vapor over the total mass times the specific volume of saturated vapor. Now, by definition, right, the triple equal sign thing here means by definition, quality is defined as mass of vapor over total mass. So I'm going to substitute that back into this equation where my specific volume, mass of fluid over total mass, that would be 1 minus quality. And then this would be quality. So let me go ahead and rearrange this equation. I get the following. Right, this is just algebra. And if I further simplify this, I can get that my specific volume is equal to the specific volume of saturated fluid plus quality times the specific volume of vaporization. So if I have my quality, if I have what the percentage of gas to total mass is for my saturated liquid vapor mixture, I can find what my actual specific volume is of that mixture as a function of the specific volume of saturated liquid and the specific volume of the saturated gas and the quality. The other sense is true where I can actually find what my quality is by knowing what the total specific volume is. Now, this equation works for any specific property. It works for any specific property. Basically, specific volume, entropy, enthalpy, and internal energy. It works for all of those properties together. All right? Okay, I hope this is clear. If some of it isn't, you can always go back in the video and check it out on a prior, just kind of rewind and relook at this. But this is uber important and something that we are going to be using a lot. All right. So if we go ahead and we look again, any value with between saturated vapor or any state within any point within the saturated liquid vapor region is going to have a quality less than 1 and greater than 0.